everybody. We're going to do a little lesson on exponential functions. We're going to start with an old, ancient Greek issue, question, paradox that I believe like Aristotle or somebody, right? We're talking long time ago. Okay, let's say this. There's a door right here. And back then, they probably didn't look this nice, but bear with me. There's a door, okay? And this door is 32 feet away from our guy, okay? Now, this guy, we'll call him X, all right? X is 32 feet away from the door, okay? And X is trying to get to the door to leave, but X is only allowed to go halfway to the door every step, okay? So, on the first step, you can go halfway there. On the second step, you can go halfway there. On the third step, you can go halfway there, etc. So, help me out here. On his first step, how big is his first step? 16 feet, right? He's going halfway. He's now 16 feet away from the door. Our man X has made a ton of progress, right? So, next up, he needs to take another step, and he gets to go halfway there. 8 feet. All right? And this process is going to continue again, right? He's going to go over here. 4 feet, he's going to go again. 2, he's going to go again. 1, he's going to go again. Well, 1 foot is 12 inches. So he's going to go again, right? And he's going to be half a foot away, right? And then how far is he going to be next time? 1/4. And then next time he's going to be 1/8. So we're starting to realize this in class, right? You guys are starting to revolt on me, right? Is our boy X ever going to actually get there? No, he's only allowed to get halfway there. And he's getting close. He's getting crazy close. If you squint your eyes, it probably looks like he's there. But is he actually there? Very, very, very interesting. All right. As strange as a start as this is to our lesson today, this is going to be super, super, super relevant, I promise you. So here's what we have. On your notes here, we're talking about exponential functions, and that's this word right here. Now, this isn't super obvious. So if I was you, I might just write exponential like right here or something, just so that it's easier to find in your notebook, just because I don't think there's a very good title on there. We're talking about exponential functions. And what you're looking at down here is our car shape, okay? We've got, here's the car with the X in it, with the little H. If you don't know what I'm talking about here, go back and watch our transformations of graph video. I promise it'll help you out. And so we've got H, K, we've got A, we've got B. Now, they use a minus H. We use a plus H. I mean, it's the same thing. It doesn't matter. But everything is going to work exactly the same for exponential functions, so help me out here. H is the what shift? What do you think? I love it. Horizontal shift. And so, of course, K would be the vertical shift. But remember, our H, our horizontal shift, is backwards of what we think. So if a plus number would actually shift us left, and a minus number would actually shift us right. For vertical, though, it is not backwards, so a plus goes up and a minus goes down. So yeah, that's exactly the same as before. If A is negative, we've seen that before, okay? What is a negative A going to do? Flip it, right? Maybe a more fancy word is to reflect. But yeah, it's gonna flip us over the axis. And it's going to be the x-axis in particular. If A is bigger than 1, we're doing a stretch. If A is less than 1, we're doing a compress. Okay, we've literally done all of these notes already. Okay, we've done this for 6 different types of questions. We've done it for linear, quadratic, absolute value, square root, cubed. Here's our newest one, number 7, exponential functions. Okay, now everything looks very similar, right? Everything looks very, very similar. Now, there is something different though. B. Okay, we've never heard of B before. In the past, B meant y-intercept of a y equals mx plus b, but that's not the same anymore. And make sure that you're cool with this, okay? This is an x that is in the exponent. You guys noticing that, right? That's why it's called exponential, because we have an exponent. And so, do me a favor, you guys in class, get out your computer. We're going to use Desmos quite a bit today. Let's go and figure out what does our parent function look like in Desmos. Okay? So, we're going to go to Desmos. We're going to take away the k. We're going to take away the h. We're going to take away the a. And we're going to not really know what b does. So, we'll leave b in there. Okay? So, let's go to Desmos. Oh, my face is back. Wish I could shrink this. All I can do is make it bigger. So over here, we've got y equals b to the power of x, right? Now, y equals b to the power of x. Desmos doesn't know what b is, so we can add a slider for b. And so I've done that. And look at what we got here. What is this? It's just a flat line, right? It's not very exciting at all. Now let's change b. Let's make b 2. And now you can see we have a curve. Now, this is the parent function for our exponential graph. Okay, so hold on. We'll go write this later on into our 7, our 7th slot of our 8 here. But looking at this, we want to take some things in. Okay, first of all, this function is going up fast, right? Really fast. If we look at another function, okay, I'm just going to type in x squared here. This is our, I did x to the power of x. Ooh, that's going to be very, very fast. This is x squared, right? We know that that graph goes up pretty fast. Check out the blue graph. Going up even faster, okay? Now check this out. This might blow your mind a little bit. If I go to, if I change this to a 2, if I go to settings, table, oh wait, no, not duplicate, sorry, table, and then I do the same thing for the other one, right? Settings, table here. When this exponential function, let me get my head out the way. When this exponential function gets to 10 versus when this quadratic function gets to 10, right? What's 10 squared? 100, right? 10 squared is 100. So this black graph, when it gets over to 10, it's going to be all the way up at 100, right? And if I zoom out, look at that. 10, 100, easy. This, when I plug in a 10, it's going to be 2 to the power of 10. Anybody know what that is? 1,000. If I want to zoom out and find where this blue graph is going to get all the way over here to 10, I've got to go past 200, past 300, past 400, 500, 600, 700, 800, 900, 1,000. 10, 1,000. Crazy, right? So this blue graph is going up fast. Let me undo so these go back out of a table. Oh, I'm hitting undo, redo. There you go. And I've gone all the way back, so it's a B. So this black graph is our U shape. Let me go back to home. It goes fast, but not as fast as the blue graph, okay? That's why sometimes you've heard this expression like things are getting exponentially out of control, right? Or like, you're growing exponentially, or the coronavirus is spreading exponentially. Yeah, that just basically means fast, okay? And not only that, it also lends itself to this kind of slow at the start, boom, explosion, straight up, okay? Now, to be very clear, this graph is not going straight up. Like, it's not literally going straight up, but it is going up fast. Now, more importantly, is on the left side of the graph, okay? If I zoom out, what's happened on the left side of the graph? Basically nothing, right? It looks very close. If you think about it like this, if I'm moving on the right, like from left to right of this function, it's getting twice as big every time, right? Again, looking at the table, it goes 1, doubled it to 2, doubled it to 3, doubled it to 4, then doubled it to 8, doubled it to 16, 32, 64, 128. So this function is doubling if I read left to right. But if I read right to left, what is happening? 128, 64, 32, 16, 8, 4, 2, 1, 1 half, 1 quarter. If I read right to left, which we're not really supposed to do, but the function is getting cut in half, okay? So what you have here is this function. Let me undo all these here. This function here is Mr. X trying to walk closer to the door, okay? He's getting cut in half to 1/2. He's getting cut in half again. He's getting cut in half again. He's trying to get to that line. And it looks like he's there. No, he's not. Right? He's trying to get there. He's trying to get there. Oh, he's finally reached it. Oh, no, he hasn't. He's trying to get there. He's trying to get to 0. He's doing everything. He's doing everything he can to get to 0. He's not going to make it. Now, he is getting closer to 0. Like, he's getting closer, but he's not actually getting there. So this graph is still, as we're reading it right to left, this graph is still going down. It's still getting closer to 0. It's hard to tell because we're so zoomed in. It's still getting closer to 0, closer to 0. We can barely see the line between. Oh, did he touch it? No. Right? It's like the saddest story ever, right? Poor guy just trying to leave the door and he just can't get there, okay? So I'm going to go back home. We've got this interesting thing, okay? On the right-hand side, it is just booming, just absolutely to the moon, going very fast up, not straight up, but very fast up. On the left-hand side, it's basically stuck. It's stuck at 0, okay? It's trying to get to 0, trying to get to 0, trying to get to 0, but it's just not getting to 0, okay? This is our parent function, and we're going to go ahead and draw that on our other sheet of paper. So I'm going to go ahead and open up the parent functions filled. Let's get there. All right, let's fill some of this stuff in. We've got exponential is our family. Our parent function is going to be y equals b to the power of x. And our graph. This graph is kind of weird because the specifics are not super, super important, okay? But you need to make sure it looks like this, okay? Not touching the 0, not touching the x-axis, just barely above it, and then right about when we get to 0, in the, like, x equals 0, we start taking off. And we launch up, okay? I always like to think about it. You'll hear me saying this a whole bunch today. This is like an airplane taking off, right? It's on the runway. Its wheels get like an inch off, and then it just hopefully doesn't go up that steep. I think that would be a problem. But it's also very important to understand that right here, the plane is not touching the runway. The plane is not touching zero. It's getting close, but it never actually touches zero. Now, what that means is that there's a brand new thing that you've never heard of before, and we're going to need to take some notes on here. Okay? We're going to need to include, let's do it over here, a new vocab word. Okay? It's spelled like this, Asymptote. Now, that hardly looks like an English word, to be honest with you, right? It looks like a Frankenstein word where we've combined three different words together. The trick to pronouncing it is that the P is basically silent, okay? The P is there, but you're not really going to say it. Yeah, you're basically going to say asymptote, okay? It can be a little bit more of a harder A than you said at Aiden, but asymptote, 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 asymptote. You need the M, you need that little in there. But you don't need to say asymptote, right? The P is not that serious. Asymptote, asymptote, asymptote. You're going to hear it 100 times, okay? And what this is, and this is where it's a great day to have different colors for your notes, and especially for this study guide. The asymptote is a line that your graph approaches but does not ever actually touch. And so where is our line? The x-axis, right? We have an asymptote right here. Now, sometimes you might see the asymptote labeled as maybe like a dotted line, because the asymptote is not the actual graph, right? If you look at Desmos, Desmos has not graphed you the asymptote, okay? Because the asymptote is not the exponential graph itself. It's a separate line that is affecting the asymptote. Okay, so, we need to understand the asymptote, where it is and how it works, but it's not like the orange line is the exponential function. The red line is the asymptote that is affecting it. Okay, and again, the whole idea of the asymptote is that we are getting closer and closer and closer, but we will never touch it. Okay, I like to think of the asymptote as like a fiery pit of death, right? And your graph will never actually touch that fiery chasm, but it's going to get close. It's interested in it maybe, right? It might be peeking over the tip, but it will never actually get to that red line. And so, yeah, this is how our graph looks for the most part. Now, there's something else, though. If we go back to Desmos, we've decided that B would be 2. Okay? And obviously, B can be a bunch of different things. If we make B equals 3, now our graph is not doubling every time. Our graph is tripling every time. So our graph is growing even faster than before. If we do the same thing again, we make this into a table. At 10, we are already up at 60,000. Remember, when we had 2 to the power of x with an x value of 10, we were over at 1,000. With 3 to the power of x, it is 60,000. So we are growing very, very, very fast. If we do 4 to the power of x, guess what? It still looks the same, but it is growing way faster, right? If we do our little table here and we go to 10, anybody want to make a guess? It is faster. It went from 1,000 to 60,000. What are we going to be now? It's going to be higher than 10,000, girl. Probably like 1,000,000. Oof. What do we got here? 10 to the power of 6. So we've got 6 zeros. Anybody know how many 6 zeros is after a 1? 1,000,000. 1,000,000. Yeah, 1,000,000. Okay? So if I wanted to scroll up and find where where we got to 10 here, I would have to scroll up to 1 million. So these graphs are growing very fast. Now, what I've been doing is I've been making B bigger each time, right? Look how it's getting steeper and steeper and steeper and steeper. What happens if B gets smaller? Less steep, less steep. And I want you to really, really focus on this. When we get to 1, that's where we started. It's a flat line because if you're multiplying by 1 over and over again, what's happening? Nothing, right? Nothing's happening. If you're multiplying by 1 over and over again, you're not changing at all. That's why this graph looks flat. But what happens when B gets smaller than 1? Right. Now, let's say I'll go to 1/2 here. Please, mouse, please, 1/2. Oh, guess not. I'll type it in. If I'm at 1/2, instead of getting twice as big, my graph is now getting half as big, half as big, half as big. So it's the same looking graph, but it's flip-flopped, right? It's not flipped over the x-axis, but it is reversed, maybe is a way to say it. So let's go here. What I would do is I would take a different color yet again. I would draw another line that looks like the airplane is landing. But it also needs to be a bit, my line's not very good because it needs to get close to that asymptote, right? It's kind of like a magnet, the asymptote. Oh, that's much better. That asymptote is just pulling the line closer and closer and closer and closer and closer. So here's a very important point here. This is what we're going to write here. If B is greater than 1, that would look like your orange graph, right? If you're doubling, if you're tripling every time, you're going to be growing super fast. What makes our blue graph? B is less than 1. And of course, we saw when B is 1, it's not really a graph, right? It's not really interesting either way. So you'll never see a question where B is equal to 1 itself. Okay, now the very last thing we're going to put on here is that we learn fancy words for this, okay? If B is greater than 1, we call this growth, right? You could say like, the amount of giraffes in the safari is experiencing exponential growth, right? It's just skyrocketing, right? The giraffes, it's just working great for them, right? Lots of tall trees with lots of leaves up there, and they're just pigging out. Now, on the other side, we call this one exponential decay. And these are very specific vocab words that you have to memorize, okay? These are not just me coming up with 2 that I like. These are words you have to memorize, right? And think about that blue graph from left to right. It's decaying, 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 falling apart, falling apart, falling apart. Now, we basically understand everything that we need to know in order to just start knocking out these questions. So let's go back to our notes. I'm going to go ahead and basically delete this when I leave this page. So hopefully you got everything. There's not really a ton of stuff here, but we'll move on. So I'm going to go back. Let's go to the exponential notes. Let's go down to number 1. Let's label some stuff here, okay? Now, what can be a little tricky is if you look at this part up here, we've got A's, H's, K's, and now we have B's, okay? And this can be a little tricky because how do we tell what's an A and what's a B? Okay, the trick is B has the exponent. Okay, whichever number has an exponent on it, that counts as a B. So this 3 here, this is not an A that would tell us about stretch or compress. B is 3. Okay? And that means, what is having a b equal 3? What does that mean about our graph? We literally just wrote it down 2 seconds ago. If your b is bigger than 1, that means growth. We're going to have a growth-shaped graph. Because this graph is getting 3 times as big, 3 times as big, 3 times as big, over and over again. All right, so we've handled the 3. Now let's talk about the 5. What is this 5 going to do? Okay, is this 5 an H or is this a K? I would agree, okay? K is 5 because it's on the outside, right? This is the car up in the exponent. So if you're not up in the exponent, you're not in the car. So 5. And what does having a K of 5 mean? Right. Okay, so should be easy to graph. We need to go up 5 with a growth. But we're not going to do that, right? We're just talking about the different transformations going from there. Okay, zone in back with me, Maurice. Come on, stay with me, boy. We've got 3 different numbers here. We need to sort all these out. So, Maurice, you're up first. This is a 2, okay? Is that 2 an A, a B, an H, or K? That's an A, I agree. And so, look at your chart right above this. If your A is 2, what does that mean? Right above us, it says A greater than 1 means... Nope, that's B, right here. Right here. A greater than 1 represents a vertical stretch. Right. This would be a stretched out graph. So the A is not that important. Okay? I mean, it's going to make a difference, but what the A is going to do is it's going to turn this graph into this graph. Right? It's going to be a little bit steeper, but it's not that much of a difference. Okay? Now, Hazel, you're up next. What does this 1/4 mean? Is that an A, a B, a H, or a K? Yep, B is 1/4, and if your B is 1/4, that means so with B, that's what we wrote on our 8 little parent function graphs. Your B determines what you're doing over and over again. We're getting 1/4 as big, 1/4 as big, 1/4 as big. This is going to be a decay. Because it's less than 1, right? And then, Aiden, you've got this -1 here. Is that an H or a K? That's an H. And if your H is -1, what's going to happen? Yep, should be right 1. Nice. All right, super focus. Okay, focusing on me for 2 seconds here. I've got a super interesting question here for Rachel, the last one. 4/3. Okay, 4/3 is our B value. Make sure you guys are cool with that. Okay, 4/3 has the exponent. B determines growth or decay. Is this growth or is this decay, Rachel? Right, really tricky. Okay, this would be growth. Here's why. Okay, this is obviously why I've asked this question, why I've stressed it. You got to be careful. Fractions don't mean less than 1 every time. Okay, it's possible that you're going to get a fraction that's bigger than 1. Okay, 4/3 of a pizza looks like this, right? That's 3/3 and another third. So this is more than 1 pizza, and so we have a growth graph. You are guaranteed to see this on the test. You are guaranteed to see this on the SOL test. Literally guaranteed, okay? A fraction number that's going to trick half the kids who are sleeping to think it's a decay, but it's a fraction bigger than 1, which means it's a growth question. All right. Let's do 2 of these graphs, and then we will be done with the notes. We're absolutely killing it. We're going really fast. Here we go. This function, it's exponential. Aiden, is this growth or decay? Growth. And how'd you know it was growth? Because this b is bigger than 1, right? I agree 100%. Then I also see this 5, and I notice that we're going to need to go left 5, okay? So let's do our graph. We need to be, basically, our parent function looks like this. Asymptote with a graph that about 0 goes up, right? What we need to do with this is slide it left 5. If we slide the asymptote left 5, it doesn't go anywhere, right? It's like putting a ruler on the ground and sliding it left, still on the ground. So, yep, our asymptote is still going to be right here. Our graph, which normally goes up about 0, is now going to go up about -5. Oh, that one wasn't so good. That one wasn't so good. Come on. Focus, focus, focus. Perfect. Right? It still looks like an airplane taking off. It still is very close to the asymptote, but never quite touching it. That's our graph. Okay, we go to Desmos. Make sure that you try typing this in because this is trickier than it looks. Y equals 2 to the power of x plus 5. This is wrong. Okay, we got to be careful with Desmos. Desmos is not going to stick that plus 5 in the exponent for you. Okay? No matter how much you try, right? Look, if I go up to the exponent and I press plus, drops it out of the exponent. Okay, so what you have to do is go up to the exponent, put a parentheses, and then put a plus 5. There's our graph, right? Asymptote is 0. It's launching up about -5. Perfect. Now let's analyze it. We got to do a lot of the same questions as yesterday. Domain. Is there anything preventing our graph from going left? No. Our graph's going left. Is there anything preventing our graph from going right? No. So our domain, all real numbers. A lot of times people mess up and they think there's some sort of blocker here, but there's not, right? The asymptote's on the bottom, that's it. Range. Is there anything preventing us from going down? Yeah, duh, that's the asymptote, right? That's the whole new thing that we're talking about. So this asymptote is in the way. Let's answer this asymptote question first. Where is the asymptote? It is on the x-axis. But we need a way to write that in mathematics, right? It's a horizontal line, right? So how do you write a horizontal line? You guys know? You guys know Hoy Vux? Does that remind you guys of anything? Right? Hoy Vux. Horizontal would be y equals. Vertical would be x equals. Horizontal has a slope of 0. Vertical has an undefined slope. So the asymptote would be y equals, and then what value is our asymptote at? 0. Right? It's a totally flat line at 0. You have to know that. A lot of students make a mistake here. They just write 0. They just slap a 0 on there. But it has to be a horizontal line. So make sure you have that y equals. So if my asymptote is at 0, then that is going to affect my range, right? So if the range is affected by the asymptote, the range should be from 0 to infinity. Okay, now, are we going to include 0? Does our graph ever get to 0? No, it doesn't actually get to 0. So this is different from yesterday as well, right? We can't include 0. We could also write this as y is greater than 0 with no equal sign, because we're not allowed to actually be 0. The last thing we need to do is in behavior, okay? And this one is as well, don't fall asleep on me, this one as well is important, okay? On the right side of our graph, that's over here, If I was standing over here, should I look above me or should I look below me to find the graph? I should look above, right? The graph's going up, so I should look above. I agree 100%. Infinity. Here's a trick question. Okay, this is the kind of the last trick question of the whole day to see if you're a superstar. On the left side, if I was standing right here, should I look up here at positive infinity or should I look down here at negative infinity? Is the y going to infinity? Is this green line going to infinity? The y value of infinity. Is it going up? This green line's going up. If I go to Desmos, is this black line going up towards infinity? Is it ever on the left side? Oh, don't say oh. We're doing left in behavior. All right? This was the right in behavior. We're doing left in behavior now. I'm over here on the left side. Is the graph going up?
Yes. Yes. It's not a flat line.
It's not a flat line. So, what I'm saying is, am I ever going to see this line shoot up? No. Am I ever going to see it shoot down? No. So is it going towards positive infinity? No, it's not going up if I'm looking right to left, right? As x is going over here, it's not going up, right? It's where's it going? No, where's it going? No, where's it going? No? Because I'm never going to see this graph go down all the way down here, right? Will this graph ever get here? Will this graph ever get here? So where is it heading? It's not heading nowhere. What is it trying to do? It's trying to get to 0. Where's the graph going? It's going to 0. Where's Professor X trying to get to? He's trying to get to the door, right? So this question here needs to be 0. Because that's where it's going, right? This graph is going towards 0. It's not going up. It's not going down. Well, technically it's going down a little bit, but it's not going to cross the asymptote. It's going towards 0. So check this out. Let me get rid of that arrow. The y-intercept I don't really care about. You can just type it in Desmos and look it up, and Desmos will solve it for you. I don't care about the y-intercept. But here's something that a real gamer will figure out here. Okay, you see how our asymptote is 0? Look at these answers: 0, 0, 0, 0. Right? Our asymptote is super influential, and it will basically make every single answer the same number as the asymptote. Okay, now look, some of them are going to be all real numbers. Some of them are going to be infinity. But if 0 is the asymptote, it's going to affect a whole bunch of stuff. We're doing one more, and I'm going much faster, so make sure you keep up. Is this growth or decay? Hurry. Decay. I agree 100%. And decay is going to be like the airplane landing. What does this minus 2 do? Moves it, yeah, but where's it going? Nope. Down. Down 2, right? The 2 is not with the x, so it's an up and down. It's a k value. Now, if I need to move everything down, is my asymptote going down? Yep. Yep. Everything needs to go down, right? My decay graph needs to look like a decay graph, but it's not stopping at 0 anymore because there's not an asymptote at 0. My decay needs to go all the way down, almost to negative 2. Okay, whip that graph up for me. Your asymptote is at negative 2. Your decay is approaching negative 2. Make sure it's going towards negative 2, right? A lot of students will put this. It's not going to 0 anymore. It's going towards that asymptote. Okay, and the asymptote got moved down. Now, knocking out domain and range. This is easy. Is there anything stopping my graph from going left? No. Is there anything stopping my graph from going right? No. So what's the domain? All real numbers. I'll give you a hint. It's always all real numbers, right? There's nothing that's going to stop a exponential graph from going left or right. Now range, okay? Is there anything preventing our graph from going up and down? Yes, of course, the asymptote. So what is the asymptote? Where is the asymptote? At -2. How do I write that as a line? Y equals -2. And again, think about it like this. This number, -2, this is like your $1 million number. We're going to use this for almost every single answer. Let's go back to the range. Is it above -2 or below -2? We should be above -2. So our range should be from -2 to infinity. Are we going to put the -2 in parentheses or brackets? Parentheses, because we're not actually getting there. -2 is not included because he's trying to get there, but he's just never going to get there. It's a very sad story. Now, this one's a bit different, okay? As x goes to infinity, that's on the right side of the graph. Where is the green arrow headed? Well, it would be 0 if our asymptote was a 0, but our asymptote is down, so -2, right? We're going to use this $1 million asymptote over and over and over and over and over again. And then on the left side of the graph, when x is going to -infinity, where are we going? We're going up. So it would be infinity. So basically, you're always going to have, for this type of question, asymptote has the -2 in behavior. One of them is -2. The range, -2. Okay? That is exponential. That is your new parent function. That is your new type of parent graph. Now, one thing that I'll give you as a really, really nice hint, the very last thing I'll say, I promise, is that your asymptote is connected to which of these letters? A, B, H, or K? K. Okay. Your A is stretch compress, doesn't have to do with the asymptote. Your B is growth decay, doesn't have to do with the asymptote. Your H is left and right. Dragging this line left or right doesn't do anything. So it is the K that affects your asymptote. So your asymptote is going to be Y equals K. Whatever that K is, that's your asymptote. Okay? If there's no K, it's going to be 0. If K is 5, it's going to be Y equals 5. You could add this part Y equals K, to your little study guide if you wanted. That's something I would recommend that you do. But that's it. That's everything that could possibly be about exponential functions. Hope it helped.